All right, so today we will be covering the rational zero theorem. So just a brief overview before we get into examples. The rational zero theorem, it gives you a list of potential zeros. Okay, so the list that we have, it will not be all of the actual zeros, just the potential zeros. Okay, and it's used on a polynomial function with integer coefficients. And finally, if the function has a zero p over q, then p is a factor of the constant term and q is a factor of the leading coefficient. So hopefully that'll make sense when we start to do the examples. But just remember that in the numerator, that is the factor for the constant term, and in the denominator, that's a factor for the leading coefficient. All right, let's look at example 1. They want us to list the possible rational zeros. Remember that we said the zeros are going to be in the form of p over q. And basically, we said it in the write-up. For the numerators, the potential numerators, p, that's going to be the factors of the constant term. And the potential denominators, q, that's going to be factors of the leading coefficient. So if we were to label this polynomial here, which one is the constant term? Well, the constant term is the one with no x, with no variables. So that's just 9. Okay, 9 is going to be the constant term. I'll just abbreviate CT. And which one is the leading coefficient? Well, you look for the largest or greatest exponent. That's x to the third. The coefficient on that is 4. Okay, so 4 is going to be the leading coefficient. All right, so the potential numerators are going to be factors of the constant term. So we're going to write out the factors of 9. The potential denominators are factors of the leading coefficient. We're going to write out the factors of 4. All right, so we have p over q, and you're always going to use plus minus. You're always going to use plus minus, and why is that? Well, let's say you have 15, the number positive 15. We know that 5 times 3 will work. But we also know that negative 5 times negative 3 will work. Okay, and if you had, say, negative 15, you can do 3 times negative 5, but you can also do negative 3 times positive 5. So in either case, the plus minus signs flip-flop. So you want to use both versions, the positive and the negative. All right, so I start with a plus minus, and I like to write it as one big fraction at first, and then I break it up into smaller fractions. Okay, so p, that is the factors of the constant term, okay, and that's in the numerator. So if we write out the factors of 9, what times what is 9? Well, we know that 1 times 9 equals 9. And we also know that 3 times 3 equals 9. Okay, but we don't need to write the 3 twice. We'll just write it once. So these are the factors of the constant term. That's in the numerator. Okay, and now in the denominator, the factors for the leading coefficient, that's 4. What times what is 4? Well, we know 1 times 4 equals 4. And we also know 2 times 2 equals 4. Okay, but we don't need to write the 2 twice, just once. All right, and now I am going to break this up into smaller fractions. We still have the plus minus. Okay, and make all the potential fractions here. First, using the numerator 1. We have 1 over 1. We have 1 over 4. And we have 1 over 2. All right, the plus minus applies to all 3 of those. Now for the 9, we have 9 over 1. We have 9 over 4. And we have 9 over 2. All right, and finally for the 3, we have 3 over 1. We have 3 over 4. And we have 3 over 2. All right, so all of these terms, plus minus, are potential zeros. These are not all of the zeros. These are possible zeros. All right, and now cleaning this up, you want to eliminate any repeats. Okay, I don't think I see any repeats, but let's make sure. Okay, we keep the plus minus. 1 over 1 is just 1. And 1/4 we can't reduce. 1/2 we can't reduce. 9 over 1 is just 9. 9/4 we cannot reduce. 9/2 we cannot reduce. 3 over 1 is just 3. 3/4 we can't reduce. And 3/2 we can't reduce. So this right here, these are the potential zeros or possible zeros. So that's it. That's all they asked for. Okay, and in the future examples, what we're going to do, we're going to try these possible zeros. We're going to use synthetic division, or we're going to use the remainder theorem. And once you find one of the zeros, then you can begin to factor the polynomial function. All right, please pause and try this example here. And remember, for the leading for the constant term, those factors are going to be in the numerator. Okay, and for the leading coefficient, remember that those factors are going to be in the denominator. Okay, so write out the big fraction and then break it up into smaller fractions. All right, so the constant term is the one with no variables. That's -8. That goes in the numerator. Okay, what are the factors of -8? Well, we already have the plus minus, so we don't need to worry about signs. So we know that 1 times 8 will work. We know that 2 times 4 will work. And I think that's it. How about for 6? I know that 1 times 6 will work. And 2 times 3 will work. And that's it right there. All right. So let's break it up into the smaller ones. 1 over 1. 1 over 6. 1 over 2. 1 over 3. All right, and then the number 8 over 1, 8 over 6. Eight over 2, 8 over 3. All right, let's see if we have room here. 2 over 1, 2 over 6. And then it's going to be 2 over 2, 2 over 3. Finally, 4 over 1, 4 over 6. Four over 2, 4 over 3. All right, I think we can cross some of these out. Let's see. 4 over 3 we don't have. 4 over 2 is the same as 2 over 1, so that's gone. 4 over 6 is the same as 2/3. That's gone. 2 over 2 is the same as 1 over 1. That's gone. Let's see, 2 over 6 is the same as 1/3. That's gone. 8 over 2, that's the same as 4 over 1. That's gone. 8 over 6 is the same as 4/3. That's gone. And let's see, I think that's it. All right, so that cuts down our list quite a bit. So we still have the plus minus. 1 over 1 is just 1. 1/6. 1/2, 1/3. And then we have 8/3, and 2 over 1 is just 2. 2/3, 4 over 1 is just 4. And 4/3. All right, so plus minus on each one of these. These are the possible or potential zeros. All right, only thing I forgot here is to label this as example 2. All right, so that one was example 2. And now in this section, we're going to completely factor each polynomial. So this will be example 1 again, because we're going to factor it all the way. Now, before you get into the rational zero theorem, you want to see if you can just factor this without the rational zero theorem. As far as the coefficients are concerned, 3, 2, 7, 2, there's no greatest common factor there. But if you look at the x's, they all have an x term. So if you factor out an x, you want to choose the one with the smallest exponent. This here is x to the first. So I'm going to factor out an x. All right, 3x to the fourth divided by x is 3x to the third. Negative 2x to the third divided by x, negative 2x squared. You just cut the exponent on each x by 1. So instead of 7x squared, it's 7x to the first. And here we have negative 2. So, again, as far as the coefficients are concerned, there's no greatest common factor. So now we're going to move on to the rational zero theorem. Okay, and we do the P over Q. And that's going to be plus minus. And in the numerator, that's going to be factors of the constant term. That's in the numerator. So we have negative 2, and the only factors are going to be 1 and 2. Okay, that's plus minus on each one. And the leading coefficient is in the denominator. That's positive 3. And really the plus minus doesn't matter because we already have it here. And what are the factors of 3? Well, just 1 times 3. All right, and now for the smaller fractions, 1 over 1 is just 1. 1 over 3 is 1/3. 2 over 1 is just 2. And 2 over 3 is 2/3. Now this is the list of possible zeros. Okay? These aren't necessarily all of the zeros. These are just possible zeros. Now, remember, we did the rational zero theorem on this right here. So these are the possible zeros for that part of the function right there. Okay, never mind the x, because we already factored out the x. So now, how do we know which ones of these are zeros of this function? Well, unfortunately, we have to use trial and error. Okay, you have to use synthetic division or the remainder theorem. Usually we go with synthetic division. And the reason is because if we use synthetic division, we have another polynomial to use and factor. Okay, so we're going to do synthetic division and find out which ones of these are possible zeros. Now, if you remember how to set up synthetic division, you want to make the bracket and leave enough room for 2 rows. Okay, we can try any of these. Let's start with 1 because that's the easiest. And what do we do for this right here? We write out the coefficients in order with the leading exponent first. This is the greatest exponent. We start with a 3, and then a -2, and then a -7, and then a -2. Okay, make sure the exponents count down by 1. If it skips 1, then you have to have a 0 in here. All right, and recall you bring down the first term. That's a 3. All right, and then you are just multiplying. 1 times 3 is 3, and then you're just adding vertically. -2 plus 3 is 1. 1 times 1 is 1. -7 plus 1 is -6. 1 times -6 is -6. And here you have -8. That is your remainder. Okay, if you have a remainder of -8, then that means it's not a 0. All right, we're looking for a remainder of 0. So that one did not work. All right, and now we have to keep going, unfortunately. We have to keep going until we find one with no remainder. We tried +1. Let's do a -1. All right, you make your bracket, leave enough space for 2 rows. We're still using the same function here, so it's the same coefficients. It's going to be 3, -2, -7, and -2. All right, so just like before, you bring down the 3 and multiply. -1 times 3 is -3, and we're going to add vertically. -2 plus -3 is -5. -1 times -5 is +5. Adding here, that's -2. -1 times -2 is +2. And -2 plus 2 is 0. That's your remainder. So we are in business. We have a remainder of 0. Now, what does this mean? If we use -1 in our synthetic division, this right here is the result when dividing by x plus 1. All right, so remember, for synthetic division, you have to cut, these are the coefficients on the x terms, but you have to cut the exponent by 1. All right, remember, this is the greatest exponent, x to the 3rd, so you have to reduce the exponent by 1. All right, so this is going to be 3x squared minus 5x minus 2. All right, so when you use synthetic division, you take the leading exponent right here, and you have to reduce that by 1. So the x to the 3rd becomes x squared. All right, and remember, for synthetic division, when you use -1, that means you basically found out the answer when dividing by x plus 1. All right, so what happens here, basically x plus 1 times this equals this right here. Okay, we use synthetic division to break it up. All right, and also don't forget we still have this x here as well. All right, so you don't want to forget about that. All right, so we have this x here, and this right here, we use synthetic division, to break it up into x plus 1 and 3x squared minus 5x minus 2. So far, so good. All right, finally, now that we have a quadratic, and by quadratic, we mean the leading term is x squared. Okay, this here is a quadratic. Whoops. This here is a quadratic. We don't have to go through the process again. We can just factor that part right there. All right, so we have x. We have x plus 1. Again, if you don't know where the x plus 1 came from, it came from right here. Okay, when you use -1 for synthetic division, that's the same as dividing by x plus 1. All right, and we got a remainder of 0, so we know x plus 1 is a factor. And this here we're going to factor into two binomials. All right, we have 3x squared. So we know we're going to start with 3x and x, because 3x times x is 3x squared. And here we have -2. So it's either going to be 2, 1, or 1, 2. All right, I'm seeing a -5 in the middle, so I'm going to have the 2 right here. So I can multiply that by 3 and the 1 right here. All right, we want -5x. So I'm going to put the -2 here, because -2 times 3x will give me -6x. And plus 1 will give me +1x. All right, so this right here is the quadratic in factored form. And that is your final answer. I am going to redo that last part in case you didn't catch it. All right, but this is the original function in factored form. All right, this was the last part we had to break up. So this right here is the equivalent of the original polynomial function. All right, let's do that last part again in case you didn't get it. This is in the form of ax squared plus bx plus c. All right, this is ax squared plus bx plus c. And when we do factoring by grouping, you have to start with a times c. So that's going to be 3 times -2. And that equals -6. What are the factors for -6? Well, we want to keep going until we find a pair that adds to -5. All right, so if we do 6 and -1, that's +5. If we do -6 and +1, that right there would add up to -5. All right, so what you do here is you rewrite this, but this here replaces -5. All right, replace -5. So 3x squared, instead of -5x, we have -6x plus 1x. And on the end, we have a -2. And now we want to factor each of these binomials individually. All right, greatest common factor between 3 and 6, that's going to be a 3. And the x with the smallest exponent, x squared and x, that's just x. That's the smallest exponent. 3x squared divided by 3x is x. -6x divided by 3x is -2. And we basically have x minus 2 right here. So this is plus x minus 2 in parentheses. All right. So what coefficient is right here in front of the x minus 2? That's just 1. All right. So the x minus 2's match. All right. So we can write the x minus 2 And the 3x is times x minus 2, and the positive 1 is times x minus 2. So we're left with 3x plus 1. All right, and that's what we had originally right here. So did you have to use factoring by grouping? Well, some of you might, some of you might not. If you just look at this right here, the way I did it, I knew 3x squared would have to be 3x times x. I knew negative 2 would either have to be 1 times negative 2 or negative 1 times positive 2. So there wasn't much to mess with right here. There wasn't much trial and error. All right, so I just went from this to this. Some of you might not be able to and have to use factoring by grouping for this quadratic right here. But anyhow, this is the final answer. In all of these problems, you want to break it down until you get a quadratic. The leading exponent is a 2. That's a quadratic when the leading exponent is a 2. Once you get a quadratic, you can actually factor it with regular factoring or by grouping or the quadratic formula. All right, example 2. Once again, we want to completely factor this here. You always want to check first if you can factor it without going through the rational zero theorem. Okay, if you look at the coefficients 3, 4, 18, 5, there is no greatest common factor. Okay, and as far as the x's, they don't all have x's. This one doesn't have an x, so we can't factor an x either. All right, so please pause and start by writing out the potential zeros, and we'll go from there. Okay, we said, as always, you start out with a plus minus. The numerator is going to be the factors of the constant term. That's positive 5. So what times what is 5? Well, the only thing is going to be 1 times 5. And the denominator is going to be the factors of the leading coefficient. That's 3. What times what is 3? That's just going to be a 1 and a 3. So what do we have? 1 over 1, that's just 1. 1 over 3, that's just 1/3. 5 over 1, that's just 5. And 5 over 3 is going to be 5/3. Now, remember I said at the beginning you can use synthetic division or you can use remainder theorem. So on this one here, I'm going to use remainder theorem. All right. And our function is called h, so we'll start with positive 1. So if we do h of 1, we're plugging in 1 wherever we see an x. So that's going to be 3 times 1 to the 3rd plus 4 times 1 squared minus 18 times 1 plus 5. All right, this is 3 plus 4 is 7 minus 18, that's negative 11 plus 5 is negative 6. This is your remainder. Okay, we're looking for a remainder of 0, so we have to keep going. All right, if we plug in negative 1, what happens? 3 times negative 1 to the 3rd plus 4 times negative 1 squared minus 18 times negative 1 plus 5. Okay, negative 1 to the 3rd is negative 1 times 3. That's going to be negative 3. Negative 1 squared is positive 1 times 4. That's going to be positive 4. Negative 18 times negative 1 is positive 18 plus 5. It's definitely not 0, so we don't even have to find it. But just for fun here, this is 19 plus 5. That's 24. The point is it's not 0. Okay, these are going to be your remainders right here. We're using the remainder theorem instead of synthetic division. So really, you have to try each one until you get a remainder of 0. All right, I cheated a little bit and I looked up the answer. I know 5/3 is going to be one of them. So I'm going to do 5/3 next. So if we do h of 5/3, that means 3 times 5/3 to the third power. All right, make sure you use parentheses. And 4 times 5/3 squared. Minus 18 times 5/3. And plus 5. All right. If you don't know how to use fractions on your calculator, please learn. Okay. Either look up the YouTube video for your model calculator or see me and I'll show you how to do it. All right. But you need to be able to do this on the calculator, which I'm going to do right now. All right. And I get 0. So that's what we want. And now we're going to use synthetic division with 5/3. All right, so you start with 5/3. And you leave the bracket enough room for 2 rows. All right, and leading exponents here, you have to count down 3, 2, 1, 0, so it works. So we're going to use 3, 4, -18, and 5. All right, we have 3, 4, -18, and 5. All right, bring down your 3 and multiply. 5/3 times 3 is going to be 5. And we're adding vertically. 4 plus 5 is 9. 5/3 times 9. Well, 9 divided by 3 is 3. 3 times 5 is 15. -18 plus 15 is -3. And finally, 5/3 times -3 is -5. And the remainder is 0. All right, these are the coefficients. The highest exponent is a 3. So you subtract 1 and you start with x squared. So this is going to be 3x squared. This is going to be plus 9x. This is going to be minus 3. All right, we have that. And since 5/3 is one of the zeros, this is going to be multiplied by x minus 5/3. Okay, remember when you use synthetic division, you have to change the plus minus sign. So that's x minus 5/3. All right, now there's 2 steps. This is a quadratic. We can start factoring this. I can see these are all divisible by 3. So I'm going to factor out a 3. And this one doesn't have an x, so I can't bring out an x. 3x squared divided by 3 is x squared. 9x divided by 3 is 3x. And -3 divided by 3 is -1. Now for this right here, we don't want fractions. All right, but there's an easy trick. If you have x minus 5/3 equals 0, and you want to get rid of the denominator of 3, you just do times 3 on both sides. So this is times 3, and the 0 is times 3. All right, distributing 3 times x is 3x. 3 times -5/3 is -5, and that equals 0. So instead of this right here, we're going to write 3x minus 5, because we don't want fractions. So we're going to write that instead, 3x minus 5. All right, and now we're in business. This right here, can we factor this the normal way? Do we have 2 numbers that multiply to -1 and add to 3? Well, let's see. If you write out the factors of -1, you only have 1 and -1. Those add to 0, not 3. So we need to use quadratic formula on this part right here. All right, so for just this part right here, if we set this equal to 0 and solve for x, that's going to be negative b plus or minus radical b squared minus 4ac all over 2a. All right, this is ax squared plus bx plus c, right? So negative b is going to be negative 3 plus or minus radical b squared, so that's going to be 3 squared, minus 4ac, so minus 4 times a, which is just 1, times c, which is negative 1. And that whole thing is divided by 2 times a. And a is just 1 right here. So it's just 2 times 1. All right, negative 3 plus minus. What's under the square root here? This is 3 squared, which is 9. Let me see. This is 9. Negative 4 times 1 times negative 1 is going to be positive 4. So 9 plus 4, or 13. And that whole thing is over 2 times 1, or just 2. All right, so what are the two terms here? Well, we have negative 3 plus radical 13 over 2. And we have negative 3 minus radical 13 over 2. All right. So going back to the original, which was this right here, what we're going to do, all right, we're going to take this and rewrite it right here. All right, we start with the 3. And we factored this right here. So one of them is going to be x. Let me see. One of them is going to be x minus this one. So that's negative 3 plus radical 13 over 2. And the other one's going to be x minus this one. Negative 3 minus radical 13 over 2. Remember, these are the zeros. So you're subtracting each one. You're subtracting each one of these from x. All right, that's this part right here. And the only thing left over is the 3x minus 5. All right, so right here is just 3x minus 5. And that is your final answer. That's the factored form. All right, so this part right here was this quadratic, and we had the 3x minus 5 on the end. If you have to use quadratic formula, whatever you get for the quadratic formula, you subtract that number. Let's just say, for the sake of argument, for the quadratic formula, you got plus or minus 5. So the factored form, it would be x minus positive 5 and x minus negative 5, which would be the same as x plus 5. So whatever numbers you get for the quadratic formula, you have to subtract those from x. So I subtracted this from x, and I subtracted that one from x as well. So that's what you have to do when you use quadratic formula. The only way to break this up, was to use quadratic formula. We couldn't factor it beyond the 3. We couldn't factor it the easy way, so we had to use quadratic formula. So right here, the third example, if you use the rational zero theorem and you did P over Q, you may end up with too many possible zeros. Okay, like for instance, this one here, it's going to have 36 possible zeros. So what you want to do is use the graph to find the zeros. Okay, if you have a graphing calculator, you can use that. Or if you have internet access, you can use a website like Desmos. Okay, so what I'm going to do is I'm going to plug this into Desmos. This is y equals 5x to the third plus 20x squared minus 9x minus 36. All right, remember the f of x, that's the same as y equals. So let's go to the website and we're going to plug in this right here. All right, as you can see, I plugged in the equation right here, y equals. In case you don't know how to do the exponents, you basically hit shift 6. Okay, so if I'm on the x right here, I hit shift and the number 6, and then I can type exponents. And then when I hit the right arrow key, it brings it back down. Anyhow, if we look at the graph, okay, we can find one of the zeros. See this one here? It's in between the squares, so that's going to be a fraction. Same with this one. It's in between the squares. But right here, this one is exactly at -4. Okay, so I'm going to use that. This one right here, see that? It's a decimal, so that's no good. This one right here, that's also a decimal. But -4 is one of the zeros, so I can start with -4. All right, so from the graph, -4 is a 0. All right, so we didn't use the zero theorem, the rational zero theorem. We just got it from the graph. All right, so we're going to use -4. We're going to use synthetic division. And we know the remainder is going to be 0 because -4 is a 0. All right, make sure it counts down, x to the third squared, first power, no power. So 5 and +20, -9 and -36. All right, bring down the first term. That's a 5. And multiply. -4 times 5 is -20. And we're adding vertically, adding these at 0. -4 times 0 is 0. Adding vertically, that's -9. -4 times -9 is +36. This right here is your remainder. All right, so these are the coefficients. The highest exponent is 3, so you subtract 1, and the highest exponent is now a 2 on the x. It's x squared instead of x to the third. We have 5x squared, we have 0x, and we have -9. And this is going to be multiplied by x plus 4. Why is it +4? Because -4 is a 0. If you set this equal to 0, x is going to be -4. All right, and rewriting, you don't need a 0x, so this is going to be 5x squared -9, and this is just x plus 4. Now, we need to factor this right here, okay? There's no greatest common factor, and this one doesn't have an x, but do we need to use quadratic formula? No, we do not, because there's no x term. All right, so we can just set this equal to 0. All right, 5x squared -9 equals 0. All right, if you do +9 on both sides, you'll get 5x squared equals 9. And this is x squared times 5. The opposite of times 5 is divided by 5. So x squared is 9/5. If you take the square root of both sides, x is going to be radical 9/5. Okay, and when you do square root, you have to do plus minus when you do square root on both sides. Let's see. Square root of 9 is just 3. So that's going to be plus or minus 3 over radical 5. Right? Because square root of 9 is just 3. Can't take the square root of 5. How do we get rid of a square root in the denominator? You just multiply the top and bottom by that denominator. All right, so in the numerator, we still have plus minus. In the numerator, 3 times radical 5. And in the denominator, radical 5 times radical 5 is just 5. All right, so basically, it's positive 3 radical 5 over 5. And it's also negative 3 radical 5 over 5. So let's see. Doing a different color. The 5x squared minus 9 gets broken up. All right, so what happens here? Just like before, we do x minus each of these. So it's going to be x minus 3 radical 5 over 5. And it's going to be x minus negative 3 radical 5 over 5. But of course, the two negatives just make it positive. And what was the other term that we had? We broke up this here, and we're left with the x plus 4. All right, so this has to come down here. And we still have x plus 4. So this right here is your final answer in factored form. All right, so what we did on this one, instead of rational zero theorem, because there were too many zeros, we used a graph to get one of the zeros. Then when we got one of the zeros, we did synthetic division to break it up. We got a quadratic because the greatest exponent was x squared. And once we got the quadratic, we broke that up even further.